and welcome to Creative Coding with Maxime. Today we're going to be making this. Now, what is this? It's a golden ratio sunflower spiral. So this is basically similar to how a sunflower distributes its seeds. So if you want, you can look up a picture of a sunflower and you can see that it looks kind of similar to what's going on here. The inspiration for this came from a video by Numberphile, golden ratio, why it is so irrational. Highly recommend that. I'll put the link to that in the description. Alright, so we're going to be using p5 for this, and I'll show you how to make this. You can code along in the web editor if you want, or you can find the full source code for this in the description. Alright, let's get started. So, I like to start out by making my canvas the maximum possible size. And for this setup, we want it to be a square. So what I'm going to do is I'm going to take the min value of the window width and height, and that will make sure it fits. Boom, perfect. Alright, then what I like to do for my setup is to try and have as many values that I use as possible normalized between 0 and 1. So I like to do that for the color range by setting the color mode to 1. Here you indicate that colors go from 0 to 1, meaning to say that 0 is black, 1 is white, and that's all we need for this video. Alright, I'm also going to set no stroke because I'm just going to be using fills for this setup. Then that's it for the setup. Alright, then another thing I like to normalize is the coordinate system. You can do this by scaling by width and height. This way your x and y coordinates go from 0 to 1 as opposed to whatever the resolution was that you were working with. The use for this is that if you resize the window or if you resize the canvas, your rendering still works exactly the same. One thing to look out for is that if you do this, you want to adjust the stroke weight as well. I'm not using it, I'm doing no stroke, but be aware of that when you do this. Alright, let's set the background to black, and then we'll set the fill to 1, which, because we normalized it, as you might remember, is white. Okay, so what do we want to do? For this flower seed pattern distribution thing to work, we need to draw a spiral. And in order to draw a spiral, we first need to be able to draw a circle. How do you draw a circle? What you can do is you can use polar coordinates. And polar coordinates are a different way to describe a position than regular x and y coordinates. Instead of having the x and y position, you have an angle and a radius, and the angle will tell you the angle of the rotation, and the radius will tell you how far away you are from the origin of that vector. Now, how can we do this? What you do is, if you just want to do the angle, you take the cosine of whatever the angle is. Let's say start at 0. Cosine of the angle, and you multiply that by 2 pi because cosine is in radians. Now this you can multiply by the radius. Okay, then for the y you can do the same thing, but then you use a sine wave. Okay, now we have calculated an x and y using a polar coordinate, and we are going to draw a circle here where the radius is going to be like this. Alright, what you see now is very small. It's in the top corner here, and that's because the polar coordinates are origin is at 0, 0. If you want to offset that, and we want to do it from the middle, you can add a half And there you go. We've got our little circle here. Now you can't really see if it's drawn in a circle because we just have one angle. But if I do this a quarter, then it'll be a quarter down. If I do this a half, it'll be on the left. All right. Well, what are we going to do now? We're going to draw multiple circles in a circle. So let's say 10. I'm going to make a loop. And now what we can do for the angle is we can take the I divided by the count, and that will give us a value between 0 and 1, and there you go. Now we can draw these circles in a nice little circle here. All right, cool. Now this I divided by count I'm gonna reuse later, so I'll call it F for fraction because it's between 0 and 1. And for now we can set the angle to the F. Now, if I make this a bit smaller and get us a bit more of these, and I'll also up, let's write this down as a variable here. We'll call it radius and we'll set it to a quarter. All right. Now we've got a circle, but we want it to be a spiral. And the way you do that is by taking the radius here and by multiplying it, for example, by this f. So I'm going to make another value called dist for distance, radius. And now, boom, there you go, a spiral. So I hope this makes sense. So first we had a circle, and now over the range of this loop from the first one to the 100th, we have this f value which goes from 0 to 1. And so for the first one, the distance for the circle here is 0, so it's in the middle. And for the final one, it's 1, so then it's the full radius, which is all the way over here. And then everything in between draws a nice spiral like this. All right, well, this is a spiral where the entire spiral is divided over the whole length of the radius. But for the setup that we have, what we want to do is, instead of do it like that, like a fraction, what we want to do is we want to take the index, the number, and if you just take the number, then the angle is a whole number, which is a full rotation, so it just goes in one direction to the right. Now, if I divide this by 2, it will go in both directions. If I divide this by 3, go in 3 directions. All right, that makes sense. Now, if I do 10, it goes in 10 directions, but you can see a little kind of spiral thing going on here. And it turns out that if you divide this by irrational numbers, then the kind of pattern that comes out of this is going to be less recognizable how many different spokes you have. If you want a like in-depth explanation on this, I recommend the video by Numberphile that I talked about in the beginning, and the link for that is in the description. All right, so let's say math.pi. I think I can just do pi, right? Boom. Interesting. So you get a different pattern already, but you can still clearly see those 3 spokes. Now, it turns out that there's an irrational number that is the most irrational number, and that is phi. And that's like 1.68 something, I think. But we can calculate it so that we have full accuracy. And the way you do that is you take 1 plus the square root of 5, and you divide that by 2. Now, if you take this phi, turn this pi into phi, then something goes wrong. Square root function. Did you try to use the square root function? If so, you want to move it into your sketch's setup function. Oh. Can I do it with... Oh, right. Okay. That was kind of weird. I guess you can't use the square root outside of in the inline, but we'll just use math.square root, which does exactly the same thing. Boom. And then, sorry for the interruption, then you'll see the pattern emerging. And what's happening here is that the distribution is so that it tries to be the least spoke-ish, and therefore it more evenly distributes among the circle. And that's also the point of the sunflower, is to distribute its seeds as uniformly as possible. Cool thing here is that you can divide by 5 or you can multiply by 5, and it'll give you exactly the same shape. And I think 5 is the only number that allows you to do that, and that's probably because it's like perfectly balanced. Alright, cool. Now that we've got this, if we up the dot count, then you see a bit more. Now, what we want to do for the visual is we want to have the radius, we want to have this fill the whole thing. So now the radius is a quarter. If I do a half, you fill this, but you still have the things missing in the corner here. So instead of having the radius be half, we need the radius to go all the way to the corner. Now, what is that? That is, if you remember Pythagoras, that is the square root of a half squared plus a half squared. Well, let's write this out. So we say, I know we can't use squared here, but just for, well, I'm going to have to use math squared, yes. Square root, the square root of a half to the power of 2, I'll just write with this, plus a half to the power of 2. Well, a half to the power of 2 is 25, so 0.25 plus 0.25 is 0.5. So the radius here is the square root of 5, and that gives you exactly this length so that it neatly distributes everywhere. Now, you'll notice that there's more seeds here in the center than on the outside, and to fill this space up nicely, what we can do is we can take the radius for the circle and we can multiply this by the fraction, the f, because the 0 is the one in the middle, and then it goes out all the way to there. So if you multiply it by f, it gets smaller in the middle and larger on the outside. And now we can make it a bunch smaller. Let's turn this into a variable, call it dot size. Let's say dot size is, alright. Then if we up the count to 1,000, voila, there you go. And that's the visual that I showed you at the beginning. I hope that was clear, and stick around for the second bit of this video, where I will show you how to animate this and how to color it. Alright, continuing where we left off, I'm going to show you how to animate and color this render. So first, what we want to do is we want to be able to have to introduce time. For that, I'm going to make a variable called t, and I'm going to have a constant that tells me how many frames is a full cycle, and t is a normalized value, like my other values. Oh, what I wanted to make clear, I'm not sure if I was clear before, the angle that I use here is another normalized value, usually, and that's why I multiply it by 2 pi, so that you get the radians. And that means that it's not like from 0 to 360 or from 0 to 2 pi, it's from 0 to 1. And so 1 is a full cycle. Oh, and when I was saying the radius for this to make it fill all the way is the square root of a half, not of 5.5. Well, you get it. Alright, cool. Back to the time. What we want is we want to know how far along we are along the 1,000 frames, and to do that I'm going to make t equal to hold up, let me see. Yes, what I'm going to do is we've got frames here. No, sorry. We've got the frame count which is a variable to tell you how many frames it has been since the start of the render, and we'll divide that by the total amount of frames. Now, to make sure that it loops when we have a full thing, what we can do is we can do the frac, which gives us the fractional component so that it goes from 0 to 1, and then when it goes over 1, it goes back to 0 and stays within 0 and 1, and it loops forever. Now, this t variable can now be used to animate things. So, for example, let's take the radius here, and we'll do this times t. And now they slowly fade in. Alright. Another thing that we can do is we can multiply the count by t. And then you get a zooming out effect. Interesting variations to this is that if you don't do it with the count variable, but just with the number in the for loop here, you can have the thing slowly grow. It's pretty neat. And if you also do it with the count, then you get a combination of the two, which has its own appeal. But we're not going to use that for this animation. I'm just going to do the regular t. However, instead of using just a t, I want to make this loop. And with this thing, it just goes on in one direction forever. So what I'm going to do is I'm going to use one of my signal functions. And I will show you how that goes. First, what I want is I need a normalized cosine function. I'll call it cos n. And it's normalized both in its phase and in its amplitude. So usually cos goes from 0 to 2 pi, or the amplitude, not the amplitude, the phase. So here we normalize it by multiplying it, so we can just do a value between 0 and 1. And then now the output still goes, the amplitude in this case goes from -1 to 1. So if we multiply that by a half, it goes from -1/2 to a half. If we add a half, it goes from 0 to 1. And so that will stay within bounds. And now this I can use for my favorite signal function, which is the inverted normalized cosine, which is exactly the same thing, but then 1 minus cosine phi. And that way, if you imagine a sine, it starts, well, if we had a normalized sine, it would start at half, go up, go down, and then end at half. If you have a cosine, it starts at 1, it goes down, and then it ends at 1. If you do the inverted cosine, you flip it, it goes from 0 to 1 and back to 0. And that's a very nice curve for animating things with. And so if we do that here, put the t in it, what you'll see is that this now zooms out, and then it will slowly zoom in again. There you go. Yes, for those that pay very close attention, you might notice some dots in the corner here popping in and out, and that's because the length that we had here, the square root of a half, goes all the way here, but then the radius of the circle needs to be added as well to make sure that that always fits inside. So I'm just going to add that size to this. I think that should work. Thing you can do is, it's nice to have t as a time, but if you want to have more control, if you want to scrub it, what you can do is you can say mouse x divided by width. That way you can control the animation of your mouse. Alright, so now we can see that the dots in the corner here, well, I can't point to it with my mouse because then it goes away. The dots in the corner here, they pop in and out exactly when they need to, so that's perfect. Alright, excellent. So that's a cool thing to animate. Another thing we can animate is the dot size. And what we can do is we can have the dots grow in size and then have that move out from the center. Alright, how do we do this? Well, we can use another signal, and I'm going to write that down as a variable. Sig is cos n of f. Alright. And what that will give us is f is 0 at the center and 1 all the way out here. So if we use this sig and multiply this by multiply it, let's see, yes, multiply it, then we will see this banding kind of pattern. Like in a circle here, it's very thin, and then it gets thicker at the edge and thicker in the middle. Now this effect we can have move by taking not just a fraction, but adding time to that. Now you can see it's slowly moving over time. It's not super clear. I'm going to multiply it by 6 to show it a bit clearer. And I'll do the mouse control thing. This is a little slow. Ooh, okay. Now you can see that there's this sort of like ring effect, which goes inwards if we move forward in time. Alright, I want to make it move outward, so it looks like a sort of bloom-ish kind of thing going on. Alright. So basically what's happening here is what you can imagine is the cosine wave, normalized cosine wave is going through this, and the thickness of this is like the sine wave, but instead of like going up and down, it goes in the z direction, sort of. You have to like imagine it inside the I'm not making it much clearer. Well, one of the things that you can do with signals like this is you can make them a bit sharper. You can make the effect a bit more pronounced by doing it to the power of something. So if I do this to the power of 2, then you will see that there will be more black and less white. It will be more subtle like this. Alright, now if I want this to have the effect that I have in mind for this animation, I should up my dot size. And now, oh, I probably need to up my dot count as well. Oh, you're starting to see it. Okay. Now where it gets thicker, you get these this big band. Alright, so that's pretty hypnotizing. But we can make this a bit prettier by adding color. And the cool thing with the color is that we can animate that as well. So, how do we do this? You can set the fill to a color, and what I'm going to do is I'm going to have a variable for the hue, the saturation, and the light value. So I'm going to do this in HSL, which means that I'll have to change my color mode to hue, saturation, light. Alright, so hue gives you the color of the rainbow, the wheel, from red to all the way to blue, and then black to red. Saturation is how much of the color is there. I go for full set for a lot of stuff. Probably shouldn't if you want to be a bit more subtle, but for now this is perfectly fine. And then the light will you can blend it to white or to black. Alright, now you can set this as a color by doing the fill, put in a color object, give it the hue, saturation, light. Okay, to make that clear, I'll separate it so it wants color. Let's make this like this because color is already defined. And I'll set the fill to that color. Okay, now what do we want for the hue? For now, let's set it to 0 and this to a half. Now it's red. Alright. What I would like to do is I want to have it go through the hue using the fract again, like before, and I'll multiply that by a half so that it's not. If you do full, you get a full rainbow. Gets a bit much, but if you do it by a half, you only get half of the rainbow at any time on the screen. Sorry, a half there. Alright. Now you can see that it's always the same colors, and I want to change this over time because it's red in the middle and green on the outside. So if I add 2, And I want to take the fract again so that it doesn't go over 1. Use a circular value, so if it goes further than 1, then it goes back to 0. 1 and 0 has the same values, both red. Alright, starting to look better. Now if I take the lightness, and if I take this signal value, which now corresponds to the size of the radius, the radius of the circles, the dot size. So when this is full, then they're really big, and when this is 0, then they're not visible at all. If I use that signal, I put it into the light value. I'm going to do that by, say, this, and add 25. So it's minimum is 25, and then max is 0.85 lightness, which goes along signal, then you get this nice bluing effect. And yeah, that's what I wanted to show today. I hope you like it. There's many things you can vary, play around with. The code for this is going to be available. You can edit it yourself in the P5 web editor. Go from there, and yeah, let me know if you make anything cool with it. All right, bye.